Hello, my name is Erica Pratt. I'm an assistant professor of biomedical engineering on the Charles River campus, and my laboratory develops multimodal tools for minimally invasive molecular diagnostics, particularly focused on liquid biopsy. So liquid biopsy is an umbrella term that encompasses a variety of analytes that are shed from the tumor into the peripheral circulation and other body fluids. This includes circulating tumor cells, DNA, extracellular vesicles, microRNAs, etc. All of these analytes are extremely rare. However, they do have two key advantages compared to a traditional invasive tumor biopsy. The first of which is blood is readily accessible, so we can perform repeated testing and we can monitor tumor response to therapy in real time. The second is that based on the best literature that we have now, most lesions in the body produce some type of circulating biomarker, which means we can use liquid biopsy to detect occult metastases and potentially use that information to deliver earlier, more targeted therapeutics to those patients. And we have a growing body of literature that suggests that we can do exactly that. And for those reasons, I consider liquid biopsy to be a central pillar in our arc towards personalized medicine, where we move from standardized therapeutic regimens that are assigned based on tumor type and stage to instead using a patient's own tumor information to guide therapeutic decision-making. And if we can do that with a simple blood draw, then we can now update that information continuously throughout the entire cycle of that patient's care, from diagnosis to definitive treatment to the emergence of resistance, metastasis, et cetera. So my laboratory has two main thrusts to try to accelerate us towards this goal. The first is analysis of circulating tumor DNA and how we can use that in early stage disease as a monitoring tool, particularly for patients who have undergone a resection and are at high risk of recurrence. The technical challenge here is that the concentration of circulating tumor DNA post-surgery is quite low. So we've developed some targeted enrichment tools and strategies that allow us to analyze and characterize these samples and derive meaningful information about patient outcomes and probability of recurrence using a very limited amount of material. And in my group, we continue to expand on ways to kind of maximize the depth of information we can extract from these samples, from improving our targeted enrichment strategies to incorporating computational approaches so that we can increase the multiplexing capacity of our panels. And through the integration of these two, we can not only perform highly multiplex profiling of clinical samples, but we can also perform repeated profiling of the same sample without exhausting it, which is essential for increasing our assay robustness, but also opens us up to performing orthogonal analyses using the same sample. The second key area of interest in our laboratory is post-translational modification enzymes and the critical role that they play in tumor cells' ability to respond nimbly and quickly to changes in their extracellular environment. To be able to measure the activity of these enzymes in a physiologically relevant way, we develop these cell deliverable peptide-based activity reporters. We have custom in silico bioinformatics pipelines that allow us to engineer these probes to be highly selective, which is being shown on the bottom, where we can come up with artificial probes that are selectively modified by our enzyme of interest. They're not modified at all by off-target enzymes, even those in the same family that have very high homology catalytic domains. And interestingly, if you compare probe A and B, these optimized substrates often outcompete peptides that are designed based on an endogenous protein substrate. We're also very interested in how we can improve the delivery of these probes into primary tumor cells. How can we engineer these probes to be cancer selective? And how can we develop next generation high sensitivity readouts so that we can analyze tens of cells to single cells? And as always, I'm always interested in collaboration, so please feel free to come up and talk to me afterwards. And I'll stop here. Thank you so much for your time.